Daniel. I am the head of developer relations here at Cerebras, and my job is basically to organize amazing events like this and create opportunities and let developers know, hey, Cerebras is amazing, and it's a great platform and a great technology to build off of. So if you really need super fast inference for your application or your startup, please talk to me afterwards my talk. I would love to see how we can help and how we can power the next generation of AI applications that are out there. But today, I want to talk about how we achieve this amazing speed with Cerebras technology. And to give an idea of how much faster we are, this is a graph of every single provider out there for, that serves open source Llama models. Right now, we're 15.5 times faster than the fastest inference provider that runs on NVIDIA GPUs, just to give a context about like how fast we are. So during my presentation, I'm going to break down a couple of optimizations that we make on the hardware side as well as the software side to achieve this incredible speed. But before we get there, let me talk a little bit about what LLMs are and how they work, and to really understand the fundamental limitations to speed that GPUs face. So let's first start with the basics. What is an LLM? So LLM stands for large language model. And you can basically think of it as super complicated pieces of software that understands and generate human language. So all of the AI apps you use, like ChatGPT, are all powered by LLMs. And if you break down what LLMs look like from the inside, they're made up of a bunch of layers, each performing mathematical computations, transforming the input into output. Each layer in the LLM processes input data through a set of parameters. They're also called weights. These parameters are calculated during training, and they refine the model's understanding of the input at each step. So by the final layer, the model selects the most likely output word based on the probability distributions calculated from all of the parameters that it learned during training. So what does it look like when you ask ChatGPT a question and it generates an output? Like, how does that work? So this is how it works. So LLMs generate text one word or one token at a time. So to generate the first token, the model processes the inputs through all of its layers, doing complex math associated with each layer, one after the other, to produce the first word. And then after that, it kind of inserts the last generated word into the top, and then it kind of repeats the process over and over again. The really important thing to note here is that you cannot parallelize this process of generating tokens. You need the previous token to be able to calculate the next one. And that's one fundamental limitation of LLMs. So for each layer of the LLM, multiple compute cores within the chip work together to do math on the input. And to do the math, each core needs access to the weights stored in memory to produce the output for the next layer. So the speed of memory access to get access to all the weights directly affects how quickly the model can generate text. So if you see ChatGPT loading and taking forever to like produce one word at a time, you kind of understand what's going on behind the scenes. So the next question I get is, why does the first token always take a lot longer than the rest? This is because after the first layer is processed, the model just doesn't discard all the math it did. It saves all of that intermediate outputs in a cache. And this means that the model when it moves to generate the next token, it can reuse a lot of the intermediate calculations from the first pass and build on top of it, which reduces the computational load it has to do. So this kind of caching strategy is really, really important when you're generating long and lots of text, because it allows the model to repeatedly, avoid just repeatedly doing the same math over and over again. And you can just kind of reuse what you can to speed up all the math that's happening behind the scenes. So instead, what we can do is that we can reuse the cache comp from the previous token and only calculate the new information. So this makes it super fast to generate the next token and the second, third, fourth, fifth token after the first one, because there's a lot of overlap in context that is reused to produce the next token. So that's why it's a lot faster. So what this means is that as you generate more and more text and you have larger and larger models, you start to hit memory constraints, because the model needs to store and read lots and lots of data. It has to both process the raw weight and the cache computations, which can quickly fill up available memory. So this is kind of like the problem that we're dealing with when we're talking about why sometimes models are super slow. So what is our secret sauce? Why is Cerebras so fast? So the first secret sauce is that Cerebras chips don't have memory bandwidth issues. And it's because we constructed the chip from day one to run these type of very memory-intensive workloads that are present in AI. So this is a picture of our chip. After the event, there's going to be a photographer running around the venue with the actual chip, so you can actually see how big it is. So this is a beautiful picture of our chip. It has 4 trillion transistors, 900,000 cores, and 44 gigabytes of on-chip memory. To compare that to the 900-pound gorilla in the room, which is the NVIDIA H100s, you can see the size difference. This is real like comparisons between the size difference between H100s and our Cerebras WSC3 chip. You can see the size difference here. And I'll quickly go through why this matters and why this enables us to serve really fast models. So this is an architecture diagram of an NVIDIA H100 chip. Highlighted in red is a specific core, or the thing that does the math. In an H100, there's around 17,000 cores on the chip. The problem is that the memory is located off the chip, which means that every time that one of the 17,000 cores wants to access raw model weights or cache computations, it has to kind of fetch that weight from external memory, which means it has to travel through multiple layers of switches and you have to travel off the chip to fetch it, which means that the memory channels that connect the external memory with the cores become a bottleneck very quickly. With Cerebras, we have a completely different chip design. Every single core has direct access to fast memory, which means that this design eliminates the need to repeatedly fetch weights from something off the chip, which reduces the entire memory bandwidth requirements and power needed to run something like this in production. So the weights for each layer in a machine learning model are stored in memory directly associated with a specific core. So the weights don't move. They stay put right where they're needed, where the core is going to do the computations. So this is one reason why that we don't have to deal with memory bandwidth issues when we're running models on our WSC3 chip. The second secret sauce is that Cerebras chips scale linearly with large models. You can see the large Statue of Liberty llama, right? It's so big, right? So before we get to exactly why we scale linearly versus exponentially for GPUs, I wanted to go through what it looks like when Meta releases a new model for open source. So you can go to Hugging Face right now to see what exactly Meta releases, what Melanie's team releases after they're done training a model. So this is an example of a model, Llama-70B. It's 16 gigabytes and has 40 layers. So when Meta releases this model, they release a couple of different components. They release the raw model weights in the form of safe tensors. They also release a configuration file that just shows you the architecture of the entire model. And finally, they release a tokenizer, which tells you how you should pre-process all of your data so the model can actually process your workload. So what Cerebras does when Melanie's team and the Meta team releases a new model is that we use our compiler to turn all of the layers and all of the weights into instructions for the cores to be able to do all the calculations. But we do something very different than GPUs. Unlike a GPU where data constantly moves back and forth between compute and memory, we've implemented something called a pipeline architecture. So in this design, the data flows through the chip while the weights remain stationary. So what we do is that we map the layers of the LLM directly onto the physical cores of our chip. So each group of cores is responsible for computation for a specific layer in the model. So as we process inputs, the data moves through the pipeline of cores, each core performing the computations for its assigned layer using its local weights. So this architecture allows us to efficiently scale to very large models by simply mapping more layers across more cores on our wafer directly. So what does it look like when you go to our inference app and then try and ask it to give you 50 cringy dad jokes? Like, what actually happens behind the scenes? So when you send a query, it hits a very regular schmegular server. It's a Dell server that pre-processes your input. So it turns your text into tokens that the machine learning model understands. And then it hits all of the layers that are mapped to individual parts of our chip that is stored in this beautiful Cerebras system that's sitting somewhere in California, Dallas, or some other data center. And then after it goes through each layer, it gets returned to the output. And thankfully, Llama 3.18b, which is 16 gigabytes, fits comfortably within one system. So it only takes one system to serve Llama 3.18b. But what happens when you want to host a larger model like 3.170b onto a Cerebras system that only has 44 gigabytes of memory? How do we tackle this? So what we do to fit larger models is by putting different layers of a large model on different Cerebras systems. To make sure there are no bottlenecks, we make sure that the time it takes to process all of the layers on each machine is around the same. So it's a full pipeline system from input to output to process a token through a very large machine learning model. So the reason for this massive speed advantage from Cerebras to GPUs is, as models get larger, is actually very simple. It's just physics. Multi-GPU setups look like the thing on the right. This is a commercially available solution called DGX H100. It's basically 8 GPUs bundled into one to process large machine learning models. But multi-GPU setups suffer from exponentially increasing latency as you grow the model size because of the frequent data exchange of different things like activations, weight updates, gradients across the GPU. So the difference is that GPUs split individual layers of a machine learning model between GPUs. So this problem of scaling like large machine learning models across multiple GPUs gets worse as you add more GPUs and as you host larger machine learning models. Cerebras architecture scales linearly without performance issues because it only communicates activations between wafers. It does not communicate tensors or any intermediate calculations, which requires very low bandwidth compared to things that GPUs have to communicate because we never split one singular layer of a model. So we have to communicate a lot less between systems. So this is why we can fit much more. This is because we can fit a lot more of the model on a single chip because our chip is so big and has so much memory. So this is kind of a summary of why we are so much faster when we serve all of these large machine learning models. So the third secret sauce is the thing that we just released that kind of skyrocketed our speed, which is all of the software optimizations we're doing on top of our hardware to accelerate inference. So one of the software optimizations we're doing is with speculative decoding. So let's first go through standard decoding. So when you run just a regular machine learning model, it generates one word at a time, right? So if you're generating 9 words, it has to go through the model 9 times. With this really new innovative technique called speculative decoding, we use 2 models. So we use one model, which is usually faster and smaller, like Llama-70B, and a larger, more accurate model, like Llama-70B. The idea here is that the small model quickly generates a sequence of words, and then the larger model steps in and be like, is this correct? Is this accurate? And then if it's not, it rewrites the thing that the smaller model generated, but if it's correct, it moves on to the next set of words. So in this example, the Llama-3B model generates multiple words, right? The quick brown fox jumps over the lazy dog. But after generating a couple of words, like 3 words, the larger Llama-70B model verifies whether the sequence is correct, and if it looks good, it moves on. If not, the Llama-70B larger model will adjust or regenerate the words as needed. So this technique significantly improves efficiency. So instead of making a pass for every word, like we do running one regular model, speculative decoding allows us to leverage the speed of a smaller model while maintaining the accuracy of a larger model. So Llama-70B only steps in to verify at key intervals instead of handling every single word. So when implemented correctly, there's no impact on accuracy or quality. That's the most important thing. So this is why for certain prompts, like the dad joke one, the output of Llama-3B and 70B aligns. So you can achieve very high speeds, like 3,000 some hundred tokens per second in speed. But for more complex prompts, the larger model has to correct the output of the smaller model more frequently. So on average, we're hitting 2,148 tokens per second in speed. But you might achieve a lot faster inference, like up to 20,000 tokens per second, depending on your prompt, based on speculative decoding. So here's Cerebras Inference's secret sauce. First, we have no memory bandwidth issues because of the fundamental architecture of our chip. Second, we scale linearly with bigger models. And third, we have awesome software optimizations like speculative decoding that make it go zoom. So that's my talk. If you want to read more about how Cerebras Inference is so fast, I wrote a blog post that summarizes everything, so feel free to scan the QR code. And I'll be around after, so if you have any questions or if you just want to fan out about the chip, I'm happy to talk with you. And if you want an API key to Cerebras, then please come talk to me. Happy to get you off the wait list. So yeah, thanks so much for coming to Llama-palooza. Woo!